Let's discuss how to calculate the center of mass of a system of particles with multiple objects. In the situation shown in figure, we are given with three masses m1, m2 and m3 with their respective position vectors r1, r2 and r3. Let's see how we'll find out the position vector of center of mass of this three particle system. Now in this situation, here if we wish to locate the center of mass, obviously in this situation center of mass, say it is located somewhere here, because it must lie within the triangle made by the joining the three masses m1, m2 and m3. Let us consider if a center of mass is denoted by C and the position vector of the center of mass with respect to origin is RC. Here we are required to find the value of this RC. Now, if we find out the mass moments of the three particles, we have to draw the position vectors of the three masses m1, m2 and m3 with respect to the center of mass. In this situation, if we just have a look on what will be the position vector of m1 with respect to the center, here we can see this is r1, this is rc. This position vector can be directly written as r1 minus rc. All of you already studied about vector analysis, that if two position vectors are known, then the line joining their tip can be given by one vector minus another vector. Similarly, the position vector of m2 with respect to center of mass can be written as r2 minus rc, and this position vector of m3 with respect to center can be given as r3 minus rc. Now in this situation we can say, by definition of center of mass, we know that sum of mass moment of all particles of a system with respect to center of mass is 0. So by definition we can say m1 into r1 minus rc plus m2 into r2 minus rc plus m3 into r3 minus rc. This equals to 0. Now in this expression, we can simply take RC common out, and this equation can be rewritten as M1 plus M2 plus M3 into RC. Here you can see, if we take RC common, we'll be having on the other side of equality M1 plus M2 plus M3 into RC is equals to M1 R1 vector plus M2 R2 vector plus M3 R3 vectors. So in this situation, we can directly get the position vector of center of mass as M1 R1 vector plus M2 R2 vector plus M3 R3 vector divided by sum of the masses M1 plus M2 plus M3. Now this expression for center of mass is a very important expression, and by symmetry we can say, by symmetry of this expression we can say that this can be generalized for any number of masses. Here we are having the result for three masses. This can be generalized as summation of mi ri from I equals to 1 to n divided by summation of mi from I equals to 1 to n. If there are n masses, then also this relation can be used by summing up m1 r1 m2 r2 m3 r3 and so on up to mn rn upon sum of all the masses of the system. So this is a generalized relation we can use for multiple object system in case of calculation of position vector of center of mass, if position vectors of their independent masses are already known to us. Here, if we wish to calculate the coordinates of center of mass, then also we can write, say if r1 is given as x1 i cap plus y1 j cap. If x1, y1 are the coordinates of position of mass m1, and r2 is given as x2 i cap plus y2 j cap, and so on for all masses of systems. If we are having the position vectors, these can be expressed as unit vectors form with the coordinates of the respective positions. Now in the situations, if we substitute these results in the final result of position vector of center of mass, which was m1 r1 plus m2 r2 plus and so on upon m1 plus m2, we substitute these results. Let's see what we'll be getting. Here it is m1 into x1 I cap plus y1 j cap plus m2 into x2 I cap plus y2 j cap, and so on for all masses. We can write it divided by it is m1 plus m2 plus any number of masses we are having in the system. We sum up their masses. Now if you just rewrite the position vector of center of mass as xc I cap plus yc j cap, which gives, if xc yc are the coordinates of center of mass, then rc vector can be written like this. And here on the right side of equality, here we take I cap common, so this will give us m1 x1 plus m2 x2 plus and so on upon m1 plus m2 plus for all masses this into I cap. Here I hope all of you are following. It says m1 x1 I cap plus m2 x2 I cap. I have taken this I cap common out. Similarly for j cap coefficients, we can write m1 y1 plus m2 y2 plus and so on upon m1 plus m2 plus and so on this j cap. Now on the two sides of equality, the vectors must be identical. So on comparing the two, we'll directly get the position coordinates of the center of mass of system, where xc can be written as summation of mi xi from I equals to 1 to n upon summation of mi from I equals to 1 to n. Similarly, y coordinate of center of mass can be given as summation of mi y upon summation of mi from I equals to 1 to n and I equals to 1 to n. These two results are extremely useful. Even if in a three-dimensional coordinate system, we'll look for the z coordinate that can also be expressed by the similar relation. In z coordinate, zc can also be written as summation of mi zi upon summation of mi. Same I from 1 to n and I from 1 to n. If in a 3D coordinate system, z coordinate of center of mass is also required, you can use this result.